Hello everyone and welcome to this presentation on deep learning architectures and their applications in image recognition. I, Abhinaya, will walk you through the powerful role of deep learning and transforming how the machines see and interpret the images. Deep learning is a branch of machine learning inspired how the human brain works. It uses artificial neural networks with multiple layers to automatically extract features and learn patterns from the raw data, especially images. Unlike traditional models that need manual feature extraction, deep learning handles everything from edges to complex patterns. The core architectures are convolutional neural network (CNNs) for grid-like data, images or videos. Recurrent neural network (RNNs) for sequential data like video frames or time series. Generative adversarial network (GANs) for generating new data. And the transformers for powerful attention-based processing. Deep learning powers many applications like medical imaging, face recognition, and autonomous driving, and many more. Now, let me simplify how it works. Deep learning mimics how the human brain processes the data. Earlier layer detects the basic patterns, say, for example, edges, textures, etc. The deeper layers identify more abstract shapes and objects. This eliminates the need for manual feature engineering. Now, in this, it's like how more the data we feed, the better the model performs. It basically thrives on large scale data sets and even learns from the direct examples. The methodologies and key concepts are at the core, basically, there are neural networks made up of nodes connected in layers. We have input layers, hidden layers, and output layers. Each node processes the data and passes it forward. Deep neural networks have multiple hidden layers, enabling hierarchical learning. These networks learn by adjusting weights based on the errors and improving with each and every iteration. Now let's look on the main architectures. CNNs are built for images. They scan pixels in small patches using filters to detect spatial features like edges or shapes. They're widely used in image classification, object detection, and facial recognition. RNNs, on the other hand, are used for sequential data. While these are not common for static images, they are very useful in image captioning and video analysis because they retain the memory from previous inputs. GANs are very fascinating. They have two parts, basically, they're two-part architectures. One is generator and the other is discriminator. A generator that creates fake images and discriminator that tries to identify if the image is real. This push-pull competition leads to realistic image generation, restoration, even the style transfer. Next comes the vision transformers, VITS, are the newer kids on the block. Instead of scanning pixels, they divide the images into patches and use attention mechanisms like NLP. They are showing excellent performance in tasks like remote sensing and large scale classification. Now, let me quickly compare. CNNs extract spatial features from the images. GANs are good at generating and enhancing the images. VITS processes the images as sequence of patches using self-attention. They often outperform CNNs in some tasks and they require less prior knowledge. Now, what are the applications in image recognition? Image classification, identifying what the object is in the image. Example, cat versus dog. Object detection, finding and locating multiple objects like car and people. Segmentation, labeling each pixel. Useful in medical imaging. Example, tumor segmentation. Facial recognition, used in smartphones, airports, and surveillance. Now, what are the real world applications? In the real world, healthcare uses deep learning for early disease detection from X rays or MRIs. Security system use it for surveillance, intrusion detection, and face verification. Autonomous vehicles rely on deep learning for the scene understanding, like detecting the lanes, signs, or the pedestrians. Now, what are the advantages? Why deep learning is so powerful? because it offers high accuracy on complex tasks, learns automatically without manual tuning, works well with high dimensional data like 4K images, and transfer learning allows us to build on pre-trained model with less data. Now, what are the disadvantages? Why it's not perfect? It's not perfect because it needs large amount of label data. Training is computationally very expensive. Models can be hard to interpret. Well, we call them as black boxes. And they also risk overfitting and can be biased if trained on poor data. Now, what are the challenges faced? The main challenges are high competition costs, both time and energy, over dependencies on data, quantity and quality, lack of generalization. Models may fail outside the training domain, ethical concerns like deep fakes and misuse in surveillances. Now, what are the future prospects? Explainable AI will make deep learning more trustworthy. Self supervised learning can reduce the need for labeled data. Models are being optimized for edge devices like smartphones. We are seeing the breakthrough in multimodal learning, combining vision with language sound. Most importantly, ethical AI will address fairness, privacy, and accountability. Now, to conclude, deep learning is revolutionizing image recognition. CNNs and GANs and transformers each serve unique roles. Despite limitations, deep learning's impact in areas like healthcare, security, and autonomous systems is undeniable. With ongoing research, we can expect even more intelligent, ethical, and powerful systems in the years to come. Thank you for watching. I hope you like this presentation. Don't forget to like, share, and subscribe.